calculus. It's only this easy after you've thought about it and worked it out many, many times. So, given a curve with some arbitrary parameterization gamma, our goal is to express how arc length, and in particular its derivative, depends on the parameter gamma. So then we're able to use this universal algorithm for translating physical integrals into arithmetic integrals that can then be evaluated by rules of calculus or numerical integration or what have you. Okay, and the formula is, I'll just write it down and then justify it in a couple of different ways. I'll go for arc length itself, not its derivative, and then we'll have its derivative by the fundamental theorem of calculus. But I will show that it equals the integral from a to, well, let's see. Let this be the point where our arc length equals 0. That's an arbitrary choice. We just decided that it's here. And we discover that the value of the parameter gamma here equals a. And then we want to know what the value of the arc length at this point relative to this point. And I'll just call this point, I'll just say that the coordinate of this point generically is gamma. And the arc length, so S of gamma, is given from the integral, by the integral from a to gamma, as you might expect, of the following quantity. So I don't think you find this formula surprising. So remember what this quantity is. First of all, it's nice to get back to the dot product, right? And geometric quantities. So somewhere our discussion up until now on integration was kind of detached from this analysis of curves that we did before. But it had to be connected to that at some point because R of gamma is the equation of the curve. That's how the curve is given. Until we introduce coordinates in the ambient space, it's given by this vector valued function. That's always been our starting point. So now that we're getting down to the business of actually calculating things for specific curves, it had to go back to this, and it had to go back to the few elements that we have, which is addition of geometric vectors. We don't have that here. Multiplication of geometric vectors by numbers. We don't have that here. And dot products, which we do have here. Okay, that's number one. Now you will recall that R of gamma is a vector that's tangential to the curve. And moreover, if we think of gamma as time, and of the curve as the trajectory of a material particle, what a natural way to think about it, then this quantity with a square root represents the magnitude of this vector. And because r prime represents velocity, perfectly intuitive, right? That's just the magnitude of velocity or speed. So in order to figure out how far you've traveled, this formula invites you to integrate speed over time, right? So you're right back to Physics 101, and I hope from that point of view it makes complete sense that this is the formula and it couldn't be anything else, right? And I will prove this formula to you, and it'll be an exercise in the same sort of reasoning that we did here, right? We have our starting point, which was in the middle and arbitrary, but everything else needs to go back to that starting point. So this formula needs to be proved. This intuitive argument is entirely convincing, but it doesn't bring you back to our founding principles. So, okay, so that's the point that we need to make. And from that, by the fundamental theorem of calculus, it follows immediately, and I'll just write it here. Okay, now let's get, in a calculus textbook, you don't want to mix your variables, so you would probably make this a dummy variable with an asterisk, so it doesn't mix with this gamma, that's fine. And by the fundamental theorem of calculus, we have this. And so here, I'll just make a comment once and not repeat it. So again, if you want to go to the ultimate practical end, where you can calculate this integral for a given curve, you would have to calculate this quantity. And for most problems, including the most simple ones, and maybe the only one I can think of is is the circle. But for any other problem, you would need to introduce coordinates in the ambient space in order to calculate this quantity. It would be too hard to do geometrically, to put on Archimedes' hat and figure out this quantity without introducing coordinates in the ambient space. And if you do introduce coordinates in the ambient space, then this task goes from nearly impossible to completely straightforward. Okay, so this will be the conclusion. But how do we prove this? Well, the first thing that we need to prove, once again, is that this integral does not depend on parameterization, right? Right now, you have a whole bunch of elements that depend on parameterization, namely 3 or 4. R depends on parameterization, so it's what function it is of gamma. Therefore, its derivative depends on parameterization, plus the limits of integration depend on parameterization. Everything depends on parameterization. So I need to prove to you that this integral does not depend on parameterization, okay? So I'll do that. You know what? I'll do that second. But first, let's for a moment accept that it doesn't depend on parameterization. Proving that it does not depend on parameterization is very enjoyable, and you get a lot of insight. So we'll take our time with it and we'll enjoy it. But for now, assume that it doesn't deserve on parameterization. Then how do we prove that it corresponds to arc length? Right? The same pattern we did before. We first prove when this was P that this integral doesn't depend on parameterization. And then we ask ourselves, what should we choose for P so that it corresponds to our intuitive understanding of the integral? The same question here. So imagine we prove that it doesn't depend on parameterization. How do we know that it's arc length? Well, the same way. Let's think about what happens when for the parameter we actually take arc length. Okay? And so then this becomes 0. And this becomes some value. I don't want to have too much of the same symbol, so I'll call it S0. Okay? Then let's think about what happens to the integral. Hopefully, this integral will evaluate to S0, right? That's what we want. Well, let's see what happens. It'll go from 0 to S0, because that's the parameterization we're using. And this will be R prime of S when the position vector was expressed as a function of arc length. This will be the same thing. And the integration will happen with respect to S, or as we say, ds. Okay, great. And what's special about this? The derivative of the position vector when it's expressed as a function of arc length. Well, it has length 1. Remember, that was the special feature of arc length parameterization that made the Frenet equations happen. So the integrand is 1. So we're integrating 1 from 0 to S0. Maybe I'll write it just so that you see how simple it is. So this integral, which we're about to argue, does not depend on parameterization. For this special parameterization, yields arc length. And therefore, it yields arc length for all parameterizations. Okay, so this I'm keeping. So we're going back to gamma. Let's now consider an integral from a to b. The only reason why I made the upper limit variable is because I wanted to use the fundamental theorem of calculus. But now we'll just consider a particular segment of the curve and just go from a to b. Okay, and it'll be similar to what we've done before, but also nice to see again what elements are we going to use? 2, the chain rule and the fundamental theorem of calculus. Now I'll use the same argument as I did before. First an intuitive argument, and then the formal proof. So suppose that our parameter gamma is such that it starts at 0 and ends at 1. Okay? And then we have an integral, and this is now the total length S. And it's whatever it is, which once everything is put together, we'll know that it's arc length, but it's whatever it is. So in fact, I won't even write this, because right now we're just going after invariance and not what it really represents. Okay, now imagine we do a change of variables. Now, of course, changes of variables are typically nonlinear, and maybe capital gamma equals e to the power of little gamma. It has to be arbitrary, and it can be arbitrarily complicated and nonlinear. Okay, but let's consider a simple one just because we're trying to make an intuitive argument. And let's suppose that it's 10 gamma. It stretches it by a factor of 10. I don't know. The word stretches is a funny word. Did I stretch my parameterization by a factor of 10, or did I shrink it by a factor of 10? The one thing that changed is that gamma, I don't know. It's how you define it, right? So gamma went from 0 to 1. But capital gamma goes from 0 to 10, right? So here it feels like we've stretched it. Maybe when we realize that the units now go like this, 1 is now here, and this is capital gamma equals 2, and capital gamma equals 3. So it used to be this entire curve from 0 to 1, and now it's this from 0 to 1. So maybe we'll call that shrinking. But the ultimate conclusion is let's not use words stretching or shrinking, because it invokes different intuition in different people, right? So the alternative integral, and here we'll have, okay, so one thing we observed is that the limits of integration became 10 times greater. So the interval of integration, if we looked at it in the arithmetic space, here it goes from 0 to 1, and here the integral goes from 0 to 10. So it's a wider integral. So if the integrand was the same, what's inside, then the integral will end up being 10 times larger. Okay? But let's see what happens inside. So when we're integrating, when we're evaluating r prime of gamma here, right? How do we do this? It's a limiting process where we take an increment of h and we find this difference and then divide it by h and then take the limit as h goes to 0. So the picture is, let's consider h that equals 0.1. That's a small enough h. And because gamma in the entire segment goes from 0 to 1, I think that gamma plus h would be just about this point right here. Right? That's just about right, because it's 1/10, roughly 1/10 of the curve over. And so r prime, so the difference on top would be this vector, right? And then when we divide it by h, which means multiply by 10, it'll end up being a vector 10 times as long, so something like this, right? That's r prime of little gamma. Let's do the same calculation for r prime of capital gamma. So now we're going to do the same thing, except with capital gamma. And importantly, we're doing it at the same point and taking the same value of h. H equals 0.1, right? And here, h equals 0.1 would actually be 10 times closer. You have to agree with that. Do you see that? That increasing capital gamma by the same h is, in physical absolute geometric terms, is traveling roughly 1/10 as far, 10 times as small a distance. So the difference on top would be this vector, and when we multiply it by 10, it'll be maybe this vector, right? And then in the limit, right now they're pointing in different directions because we're taking a finite h, but as h goes to 0, they will both end up being pointing in the tangential direction, except this difference, and therefore this ratio, and therefore this limit will be 10 times smaller, right? So when you expand, stretch, or shrink, or whatever word you want to use, I would use neither, parameterization by a factor of 10, that's what happens to the derivative, right? In the case of this change, it becomes 10 times smaller. So here the integrand is 10 times smaller than it is here. So the limits of integration are 10 times wider, but the integrand is 10 times smaller. So on the balance, it works out to be the same thing. So that's the intuitive reason for it. Another intuitive reason is that doing this, like for example, if I made it not 10 but 60, right? Then it's like switching from minutes to hours. Or maybe it's switching from minutes to seconds. Again, it's very hard for me to know which way it goes, right? If gamma is minutes, then capital gamma is seconds, right? Because there would be more seconds for every minute. Okay, so it's going from seconds to minutes. And we're measuring the same velocity. But if it's per second, from minutes to seconds. So if it's per second, it's going to be a much smaller number by a factor of 60. But the limit of integration would be a much larger number because we're now measuring everything in seconds. But the result will be the same distance. Okay, that's great. So I think that's great. So that's the intuitive reason for why these integrals are the same regardless of parameterization. And when it's not a linear change like this, but something more sophisticated, right, then this sort of stretching and this sort of argument works at every point in the pointwise sense. So it's just to make an intuitive argument. But now let's make the real argument. Here's our change of variables rule. Nu gamma is a function of the old parameter. Again, I'm overloading the letter. This is the parameter gamma, and this is the function that expresses it in terms of the old parameter. So we have our integral from a to b. And now we have to get to this parameter. The way the position vector depends on our parameter gamma can be obtained by the composition, by expressing the position vector as a function of our new parameter, which is the function we want to get to, where you substitute how the new parameter depends on the old parameter. This is a very subtle point. I make it look easy because I've done this 1,000 times. And I was confused for the first 990 times. Getting to this point what took the longest time, and weeks of thinking and getting it wrong and making mistakes. It's just not as easy as it looks. It's only this easy after you've thought about it and worked it out many, many times. Okay, and if you haven't gone through that labor, and I think that I'll make it as easy as possible on you, but you just won't get it until you've made 100 mistakes. So something to look forward to. Okay, so I need its derivative. So of course I'll use the chain rule. I'll do it in place. The derivative of this equals the derivative of this. Now realize this is an entirely different function. This is how the position vector depends on the new parameter. So I'm taking the derivative of a different function here, and you can differentiate the two functions because this one is a function of little gamma, and this one is the function of big gamma. And that's another element of getting this. If you're not naming the objects that you're working with, if you just rely on your calculus AP instinct of just rolling with the identity without thinking, you'll never get through it. It's really just, and one of the problems on the final will force you to do this. You just have to say, okay, here I'm differentiating position vector as a function of little gamma, and this is the derivative of the position vector as a function of big gamma. And then, of course, by the chain rule, I have to take the derivative of the change of variables function right here. Okay? Fantastic. Let's plug it in. The next step, I won't do it in place. I will take this from under the square root. It's squared under the square root, so it'll come out as gamma prime of gamma, which is a step that you have to be careful with, because ordinarily, if you have square root of x squared, this equals, yeah, so it's absolute value of x, so I can just take it out. But remember the caveat that I made? I said that everything, I've erased the curve, but the arc length and one parameter, and then the alternative parameter will all increase in the same direction. So this is a monotonic function, and its derivative is positive. So I'm leaning on that caveat. So it will come out just as a derivative without the absolute value. And now what we have here is basically a template for the change of variables formula from little gamma to big gamma. Do you remember that? I don't have the change of variables formula on the board, but we basically have a function where you have a substitution followed by the derivative of that substitution. That's exactly the pattern for, it's usually called integration by substitution. I call it change of variables. Okay, so it becomes, which is the limits. Of course, I have it erased. But if little gamma changes from A to B, that's little gamma. Then big gamma changes from capital A to capital B. In other words, limits represented by capital gamma. From A to B. There you go. It becomes the exact same recipe, but for the alternative parameter, capital gamma. Okay, and the proof is complete, and it couldn't have been complicated because, once again, we don't have that many elements to work with. And of course, it's the change of variables formula, and of course, you get the exact same thing, but for the other parameter. Okay, so we just proved that this sort of expression does not depend on parameterization, and previously we showed that if for the parameter we just happen to choose S, then this integral gives us arc length. And if this integral gives us arc length for one special parameterization, then it gives us arc length for all possible parameterizations. Okay? And the proof is complete.